And Priya, you guys got your bug figured out?
Yeah, so we had something was wrong with how we were shifting the serial input, but yeah, it's there now.
Okay.
I won't be able to go to the checkoff, but Caitlin and Michael will both be.
Okay, sounds good. Anybody else finding any sort of bugs that would be good to bring up with the whole group with regard to lab 2 week 1 checkout?
I'm not sure if you saw like our comment on Canvas in like response to your like announcement about setting up the audio. But like, yeah, right now we're like not sure if our HPS code isn't working or if it's that the sound isn't right.
Okay, I can hop on a Zoom call after this or whenever you're free to check your workflow. I've debugged this with Katie and with Parker so far, and we've been able to get it to work, but yeah, the configurations and everything is worth going over maybe.
Okay.
Okay.
Yeah, I have like lecture right after this, but.
Okay, whenever you have some time, we can log on and check things out. Saw another good bug from, I think it was from Rishi, Felipe, and Sujith's group, where we were seeing for the one node, the decaying sinusoid was very sort of quantized and squared off. It appeared to be working correctly, but there was really odd quantization. The answer ended up being it turns out that the frequency of the sine wave is related to your choice of rho. And see if I can get this correctly. The higher that your rho is, the higher frequency the sine wave. Is that right, Bruce?
That's right.
Yeah.
And as rho approaches 0.5, the sine wave approaches the Nyquist limit and goes to a square wave, decaying square wave with only 2 samples per sine cycle. So if you're at a rho of 0.25, then you can ask how many samples are there per cycle. It's not linear. I think it's square root, but I'll have to go back and look. But by the time you get down to a rho of about 1/16, you get a decent number of samples on one node. And you say, well, why such a limited range? And that is because the frequency of tiny drums is very high. They're small. Make them bigger, then for bigger rho, you'll still get a good sine wave.
So the solution ended up being reduce rho, and then we saw a nice smooth wave. So if when you're simulating one node, you see that odd sort of quantization effect, try dropping your rho value. See if that smooths things out. Katie discovered the consequences of another bug, which is if you update the drum asynchronously. So if you replace UN with UN plus 1, and then use UN plus 1 when you're updating the rest of the drum, it makes your drum unconditionally unstable. So you will get sort of high, low, weird, overflowing waves coming out. And the solution is to make sure that things remain synchronous. Does that sound right, Katie? It's about what you saw, right? Yeah.
Yeah, basically it looks like it kind of like starts oscillating the opposite way you want it to oscillate, then and it overflows, of course.
Magically gaining energy, yeah. Anyone else find anything interesting? Things going okay?
So I did have one thing that I found, and maybe I'm just doing this wrong, I don't know, but I know for part of the week 1 checkout, we had to basically time the HPS code to see how long it takes to iterate or to update each of the nodes in the drum. So I just tried to do that by basically just using the clock function in the time library in C. And I just clocked before and after to like get those values and just tried to find the difference. But with the 10 by 10 drum, the outputs of the variables were equivalent, so I kept getting 0 delay. But I know that the display itself is working, because if I added like a for loop that does nothing, I did get different values. So it's like, are we supposed to see no delay, or is there a way to configure the clock function?
So would you see only zeros, or would you occasionally get a non-zero value?
It'd
Or was it
be
only
zeros.
zero?
It was only zeros for 10 by 10.
Okay. We might have to take a look at that offline, but Parker was seeing a similar symptom. Parker, do you want to explain the symptom that you were seeing?
Well, I could never figure out actually why, and debugging exactly, like occasionally there was a value of like 10 or something that showed up, but the units are also an issue anyways, because I'm not sure if, I was going more into the documentation, I'm not sure if the minimum, well, depending on which time variable you grab, it can be a minimum of seconds. I think there might be microseconds somewhere, but it might be a little more complicated to grab the more precise values.
As far as I know, the demo code I put up grabs microseconds.
Yeah, that like when I was looking up the documentation for like getting Unix time, it was a little strange, and well, I never could get a difference in the values. Could try a long delay.
So where it was on the DSP page, right? The DSP page code calculates a time, which for me was microseconds.
Because according to like documentation for C, it's supposed to return the number of clock ticks.
Yes.
So we'd have to actually get the processor speed, but I never had a difference in clock speed, the ticks anyway.
No, according to man page on clock, it should return, as you say, ticks, but as of C99 and the POSIX standard, that has to return microseconds.
Okay.
According to the documentation.
Yeah.
Right. Well, I don't think it was outputting ticks, because if it was, I probably would have seen some difference in the before and after. But if they were exactly the same, that might be like a time difference. And if they're equivalent to like a certain precision, then the display just wouldn't show it, the internal variables.
Were you calculating the time of one sample or all the samples?
At one particular sample, I calculated the time to update all of the nodes.
Sample.
So
So
basically,
you do one entire iteration through the drum.
yes, exactly.
Have been for a 10 by 10 is on the order of like 5 microseconds or something.
You might have to look at this offline.
Yeah, sure.
Okay. But okay, we'll figure that out. Anything else from anyone? Any other issues, bugs? Okay. So I thought what might be productive to do at this point is to do, to basically just spend a lecture doing a brief review of the stuff that we've been going over, specifically related to busmasters and the audio subsystem for the past like 3 weeks or so. And I'm doing this because for a lot of classes, this would be approximately in the semester when a prelim would live. So there would probably be a review session. And I always found those review sessions extremely helpful. There's something about seeing that material again, concisely and all together that helps solidify things for me. So despite the fact that we don't have a prelim, I thought something like a review session kind of lecture might be productive at this point in time. So that's what I'll do. Unless there are other questions. If you have other questions, you can just interrupt me and we can talk about that. But I thought I would review some Busmaster content. So, let's start simple and then quickly work our way up to the audio stuff. So if we go back to the Busmaster page, which we've looked at before, I'll start the way that I started before, which is by showing you the user manual for this module. And we've seen this a few times now at this point, but I'll just remind you again that these Busmasters are pieces of Intel Altera IP that you drag onto the QSys bus. And they are a mechanism by which you can control bus slaves that you also put on the QSys bus through Verilog. So that is to say entirely on the FPGA, instead of controlling those peripherals through the HPS, which is faster. It's faster to control things through the FPGA. So when you drag one of these Busmasters onto the QSys bus and you export the conduit into your Verilog, you will find 7 new wires available for you to hook up to your Verilog. Those wires are, they are named address, write data, read, write, byte enable, acknowledge, and read data. Where, as we've discussed, the address is specifying the particular address on the Avalon bus to which you want to write or from which you want to read. The write data is, of course, in the case that you're writing, this is the data that you want to write to the bus. Read and write are 1-bit wires that just specify whether you are reading or writing to or from the bus. Byte enable specifies how many bytes you are writing or reading. The acknowledgement is what the bus sends back to you after you do a bus read or write to let you know that that operation is complete. And then in the event that you're reading, data comes back over a read data line, which you can read for 1 cycle. The cycle after this bus acknowledge goes high, and then a cycle later that data is gone. So this is precisely how this protocol works. We've again seen this a couple of times, but I'll just remind you that in the case that you are writing, then you set the write address, the address on the bus to which you want to write. You deassert the read enable, assert write enable. You set byte enable to however many bytes you want to write. You put that information into write data, and then you wait for the acknowledgement. And once you receive that acknowledgement, then you know that the bus write is complete. In the event that you're doing a bus read, then you specify the read address on the address line, assert the read enable line, deassert write, specify how many bytes you would like to read with the byte enable line, and then you wait for the ACK. And when that ACK goes high, the data is available to be gathered from the read data line, and then a cycle later that data is gone. Okay, so we can take a look at a simple example of this. And the example that we took a look at to start was one in which we were using a Busmaster to write to PIO ports. So you'll recall that in this example, what we're doing is sending a value, a numeric value over a PIO line. That value is going into a Busmaster, which is doing a bus write to a PIO port that lives at the same address as the onboard LEDs. So we can send the number 10, and then the binary representation of 10 will be written to the onboard LEDs so that 10 lights up in binary on the LEDs. And then we do a bus read from a second PIO port that lives where the onboard switches live. So we point the Busmaster to the address of the switches, read the value of those switches through a bus read, and send that value back through another PIO port back to the HPS so that we can see the value on the switches. So I'll just remind you that this is what the QSys layout looks like for this. So we have our system PLL as usual. We have our ARM on here as usual. And then we have 4 PIO ports. And I'll talk first about the two PIO ports that are associated with the LEDs. You see that the LED display PIO port, it's hooked up to the clock, hooked up to the reset lines as usual. And then we have the slave input for this PIO port attached to the bus master output. And importantly, not connected to the HPS, right? So this PIO port is in no way connected to the ARM. It is only connected to our bus master. And then we've exported this into our Verilog. And we'll take a look at that Verilog in a moment. And we've put this at an offset of hex 20 from the base of the bus master. And then in our Verilog, so once we export that, that shows up in our Verilog as LED display export, and we've tied that directly to the onboard LEDs, which means that when we write to that PIO port, we're writing to the onboard LEDs. Our other PIO port that has an LED prefix is again hooked up to the clock and reset lines. This one is hooked up to the lightweight AXI-master of the ARM. So we can send our LED command in through this PIO port, and the bus master will write that value to our LED display PIO port that lives at the address of the onboard LEDs. So these two will be used to exercise the bus write aspect of the bus master. And then we have a couple of other PIO ports that are being used to exercise the bus read. So this, oh my, hold on, I just made everything disappear. Where'd it go? All right, we're gonna just reopen it. But just like before, the switch slave PIO port will be hooked up in Verilog to the switches. So when we read from that PIO port, we'll be reading from the onboard switches. And then we'll have a second PIO port that's hooked up to the ARM so that we can communicate that value that the bus master has read from the switches back to the ARM. So we send a value in over a PIO port to the bus master. The bus master writes that to the onboard LEDs. And then we point the bus master to the switches. It will read the state of those switches and send it back over a fourth PIO port back to the ARM. So the switch slave here is hooked up to the Avalon master and exported into Verilog. And within the Verilog, we've tied the switch slave to the onboard switches. And then our other PIO port, which we've called switch state export, we send back to the HPS. So we can take a look at the Verilog associated with this. So that's the QSYS. Things get exported. We hook them up to the hardware and to various wires that we've declared within our own Verilog. And then up above, we have the state machine, which drives this bus master. And I'll remind you also, when we do the conduit export for the bus master here, that then reveals the 7 signals that we just looked at in the data sheet. So that then reveals the address, byte enable, read, write data, acknowledge and read data into our Verilog, which we hook up to our own wires that we've declared in the module above. And then the state machine for actually running this is the Verilog version of the graphic that we just looked at in the busmaster data sheet. So we start in state 0 here, and then in the event that we see a a new value coming over the PIO port where we're sending LED commands. Then we drop into state 1, and we set a register which is holding the current state of the LEDs equal to the value on that PIO port. This is just so that the state machine only runs when it sees new values. We set the data that we want to write, that is the bus write data. We set that equal to the value coming over that PIO port. We set the byte enable to 2 bytes. We want to write 2 bytes. We set the address that we want to write to hex 20, where again, hex 20, as specified in QSYS, right? This is where we put that PIO port. And then we assert the write enable line. We wait for the bus act to return. And once the bus act goes high, we'll drop into this state. And in this state, we know that the bus write is complete. So in the case that we were only doing bus writes and we weren't doing any bus reads, we could then deassert the bus write signal here and go back up into this state to wait to do another write if we were only writing. In this case, I have this dropping into state 2 where we're then going to do a bus read. So just to be clear, at this point, the bus write is complete. We've set the data, we've set the byte enable, we've set the address that we're writing to, and we've asserted the write line, and then we've gotten the ACK back. So we know that this write is complete. And we can do a read. To do a read, we assert the read enable. We want to read 2 bytes, so we set byte enable to 11. And the address from which we want to read is address 0, where that, again, comes from QSYS. We have our switch slave PIO port at hex 0 offset here. We wait for the ACK. When we're doing a bus read, remember that when that ACK goes high, that means the data is available to be read from the bus read data line. And it's available for just this cycle. So once that ACK goes high, we will set our state back to 0 so that we can wait for a new command to come over the LED PIO line. We deassert the read enable, and then we're going to store the data that we've read from that address, which recall is tied to the switches. So we're reading here the value of the switches, the onboard switches. We're putting that into a register which I've called switch reg. And then beneath all of this, I have an assign statement, which is at all times setting the value of this switch to HPS wire equal to the value contained in that switch reg. And this switch to HPS wire is tied to the PIO port, which then goes back to the ARM. So when we run this, what we expect is when we send a new value over this LED PIO line, then that value will be written to the onboard LEDs. The busmaster will then go look at the address where the switches live, get that value from the switches, and send it back. And you've seen this before, so I won't spend tremendously much time on it, but we'll just look at this. Oh, it's open in Zoom. That's fine. You've seen this before. I don't need to show you this again. So that is, as I mentioned when I was introducing this the first time, this example is for illustrating and explaining the mechanics of a busmaster. This is not really a practical example. You wouldn't necessarily write a busmaster to write LEDs and to read from switches, but you might do something like this to understand how these busmasters work. So that's the point of this. So let's consider something that's actually practical to do with these busmasters, which is control the audio codec. So let's again take a look at a data sheet. So we now want to control the audio core with a bus master. And I'll just remind you that this is where the data sheet for this lives. And if we just glance through this quickly, this is the block diagram for this audio core. Remember that the nature of audio is such that a precise sample rate is very important. So in our case, we are sampling for a new audio sample at 48 kilohertz. That means every 48 kilohertz, there better be data here ready to be output to the DAC. Now the Avalon switch fabric, right, the Avalon bus can be a little bit bursty. So in order to make certain that we have a sample ready at precisely 48 kilohertz from this bursty switch fabric, there is a FIFO that lives between the switch fabric and the audio output. So what this means is when we are writing to the audio subsystem, we are filling these FIFOs. So before each write, we're going to check if there's space in this FIFO, and then only if there is space in this FIFO, in these FIFOs, I should say, the left and right FIFOs, only if there's space there, do we write a new sample that will ultimately be output here to the DAC. So there are only 4 registers associated with this module. There's a control register which sets things up. There's a FIFO space register, which, as the name suggests, tells you how much space is in each of these FIFOs. And then there's a left data and a right data register where we put the data, which will be output from the DAC, or in the case that we're reading from a microphone, this is where the input data goes to, these 2 registers. And these registers are explained in a bit more detail down below. If we take a look at this. So what this table is telling you is where is the position of each of these registers from the audio base address. So this is telling you that the control register is at a 0 offset in bytes from the audio base address. The FIFO space register is offset by 4, left data by 8, right data by 12. And then each of these registers is 32 bits wide. And this table is telling you what information lives in which of these bits for each of these registers. So we can take a look at one that you'll be paying particularly close attention to is this FIFO space register, which lives in an offset of 4 from the base address. And you can see that the top 8 bits are the left channel right space in the right space FIFO. How much space is in that FIFO? Right channel right space. Left channel read availability, I guess, is what the RA stands for. And then the same for the right channel. And then there's some information here, some additional information here about the control register that I won't get into at the moment, but is here if you care to look at it. Questions about this? Okay, so then we can consider what a bus master for controlling this module would look like. And going to close this and move to the DSP demo. So this is the demo I showed you where it creates different tunes. Right? We played a few tunes through the Zoom interface. And we'll look at the QSys for this particular project. I hope this is helpful. I'm kind of taking my best guess here at what I would think would be helpful at this point in the semester. And I think this is what I would find to be helpful. but if I've guessed wrong, just let me know. You can even let me know anonymously now if you want to. I put an announcement on Piazza, but there's an anonymous feedback Google form embedded on the Canvas homepage. So if you have any feedback, you can feel free to put it there. In any case, so what we're looking at now is the QSys layout for the audio DSP example. So there's some stuff in here that's very familiar. The system PLL as usual. We have the ARM on this bus. The AV config module. I'll show you after this the actual data sheet for the Wolfson codec. It's a separate piece of hardware that's controlling this audio interface. This AV config module is setting up that external piece of hardware. It's doing so through an I2C interface. But when I show you the block diagram for that Wolfson codec, that external piece of hardware, you'll see that there's a whole lot of options available for how you want to use this thing. And this AV config allows for you to set all of those configurations within QSys. And then through that I2C bus, it'll set up that Wolfson codec for you. So you can see that, you know, if we were to double click this, there's a bunch of options available here for precisely how you want to set things up. And then I can leave that open. And then we set up the clock reset lines. Pointed this slave input to the AXI master. And then exported this conduit here, which I'll show you in the Verilog in a moment. We've tied to the I2C lines on the FPGA. And then the audio subsystem is on here. And I will just point out that we have the audio slave hooked up to the bus master here. We have it also hooked up in this example to the lightweight master, which means you could, in principle, drive this from the ARM. We're not going to in this particular example, but in the drum simulation from the HPS example that you will be implementing a nonlinear row 4 for your week 1 checkout for lab 2. In that particular case, you are in fact driving the audio subsystem from the HPS. In this case, we could drive it from either because we have it hooked up to either. We won't drive it from the HPS. We'll drive it from the bus master. Okay. Then we have our bus master here. Again, the master is driving the audio slave input, and we've exported our conduit so that we have access to all of those levers to pull on in order to actually drive the bus. And then a PIO line just to, because we don't have access to pushing buttons, we are emulating pushing buttons through PIO ports. So this PIO port is the equivalent of a reset line. And then through that PIO port, we can set essentially the frequency that we want the DSP to synthesize. So we can take a look at the Verilog. And I'll start by looking at the computer system module. And I'll just show you some of the things that we've generated. So that reset PIO line, we've just tied to a wire that we've declared up in our own Verilog, which I'll show you in a moment. You can see that the 2 AV config exported conduits, we've, as I've mentioned, tied to our I2C lines. And then our audio subsystem, which we've exported into our Verilog, we tie this to various pieces of actual hardware on the FPGA. Very much similar to in the previous example, we tied our PIO ports to actual LED hardware and actual switch hardware. In this case, we're tying our QSys generated lines here to actual hardware associated with our audio codec. Okay, so if we were to scroll up to the top of this, we could see all of this actual hardware declared as inputs and outputs for our top level module. So these are actual wires going out to control that Wolfson codec that's external to the FPGA. Okay, and then we build a state machine that drives this bus. And in this case, we're doing digital, direct digital synthesis, which is to say we're generating sounds. So we're only doing bus writes. We're not reading from the audio system from something like a microphone. There are examples of doing that on the course website. So full audio loopback examples are on the course website if you want to see how to do that. But we can take a look at the state machine. So in the case that we're in a reset state, then we do a bunch of things. We set our state to 0. Read and write enables go to 0. We zero some timer that's really just being used to make sure that the state machine's running. And then we set this reset status register to all ones. And I have this register tied to the onboard LEDs so that all the LEDs come on and reset so that we can see visually that the system's in reset. But okay, suppose we're not in reset, right? Then the first state that we drop into is state 0. We want to do a bus read, and we're going to be reading specifically from the audio FIFO address. We want to see if there is space available in the FIFO to write a new audio sample. So we're reading from this audio FIFO address. Where does this come from? So up above, you can see that the audio FIFO address is at hex 3044. Well, you can first of all see that the audio base address is at hex 3040. And that is because in QSYS, the audio system we've placed at hex 3040. Right, so that is the base address for the audio system. But then you can furthermore see that the audio FIFO address is at an offset of 4 from that base address. That is straight out of the data sheet. Where you can see that the FIFO space register is at an offset of 4 from the base address. Okay, so that's where that's coming from. And you can see similarly based on that data sheet, the left address is at an offset of 8 and the right address is at an offset of C, right? All those two are all from the data sheet, offsets from this base address. But okay, so we're in state 0. We're doing a read from the audio FIFO address. We set the read enable. We want to read 4 bytes. And then we set the state to 1, and we wait for that bus ACK. When that bus ACK goes high, then the data is available to be read. So when this goes high, we're going to set our state to 2, and we are going to shift into this FIFO space register the bus read data shifted by 24 bits. Why shifted by 24 bits? This again is a data sheet thing. It's because if we shift by 24 bits, we are taking a look at how much, at the FIFO space for the write. I'm using both versions of write. So the WRITE write FIFO left channel. We're seeing how much space is available in that FIFO by shifting this whole thing by 24. And then we deassert our bus read. So the next step that we take is conditional on how much space is available in that FIFO. If there is less than 2 spaces in this particular example, it could be less than 1 space, but if there's less than 2 spaces available in that FIFO, we go back to state 0 and we try again. We wait for more space to be freed up in the FIFO. In the case that there is space in the FIFO, we set the state to 3. We accumulate some phase for our direct digital synthesis. This line here is tied to a sign table down below so that we can get a DDS value out. And then we want to write that data to both the left and right channel FIFOs. So the data that we're going to write is the output from our sine table. The address to which we are going to write is the audio left address, the left channel address. We're going to write 4 bytes, and we set the write enable to 1. We wait for the bus act to go high. Once that bus act goes high, we're done with writing the, what did I just say, the right channel or the left channel? The left channel. We drop into state 4. And then we write the same value to the right channel. And remember, I mentioned this last time we went over this. It turns out you have to write this data to both the left and right channel. If you write to only one channel, you get silence out. So you need to write the data to both the left channel and the right channel. If you're setting one of these systems up and you don't hear anything, make sure you're writing to both channels. So then we write the right channel, wait for the ACK, and go back to state 0. Okay. So in your case for lab 2, what's going to change about this is here, this bus write data, the data that you're actually writing, this is going to be the data that you get from some drum simulation module. So your module, your drum simulation will produce some audio output, and that will go where, in this example, the direct digital synthesis output is going. Okay. So then the last thing that I want to show you is, and this is directly relevant to lab 2, is driving this audio system from the HPS. Because part of your checkout for week 1 for lab 2 is to modify some existing HPS code that does a drum simulation to include a nonlinear row and to time that drum simulation. And we were talking about that at the beginning of this lecture. So if we go to the DSP on DE1 SOC page and take a look at this section here. Okay, so the project associated with the HPS code that I'm about to show you is linked here. Verilog lives here. Take a look at this if you care to, and you should. But I'm just pointing this out because this is the Verilog that you should be putting on the FPGA to run the HPS code that drives the audio system. And then the drum code lives here. Let me just put this in a syntax highlighting place. So this is doing mechanically is the wrong word, but logically the same sort of thing that we just saw for the bus master that lives fully in Verilog, which is to say it is, you're doing this memory mapping to set the audio base address, the FIFO data address, left data, right data, right? So you're writing to all the same registers, you're just mapping them into C on the HPS side. And then down here, you are checking the amount of space that's available in the audio FIFO. Again, shifted by 24. We're looking at that one specific part of this register. And then in the event that there is space, you are doing a drum simulation, which is generating a new audio output. And you are writing that then to both the left and right channels, which will produce a drum sound. This does not include the nonlinear row. So for your week 1 checkout, you are basically getting this code to run. So step 1 is load the Verilog onto the FPGA, load this HPS code onto the ARM, compile it and run it, and make sure you get a clang back out when you run it. It should simulate a drum. And then to implement the nonlinear row in this C code. And I want to point out one thing before I run out of time about the Verilog, which is that the one thing to be cautious about, and I looked at this with Parker in last week's lab section, is this will require one simple modification, which is that if we were to look at the QSys, like the previous example, this audio system is tied both to the ARM and to a busmaster. So it can be driven either from Verilog or from the HPS. And here in this line here is designating whether the HPS or the ARM is driving the audio system. You want for the ARM to be driving the audio system for this particular part of the checkout. So instead of making that conditioned on the state of some switch, which you can't touch, set this reset to 1. If you just assign this a value of 1, then down here in the state machine that drives the audio system in Verilog, you will just be holding this state machine in reset, and the audio system will get driven by the HPS. So that's the only modification that has to take place for this Verilog. Okay. Any questions? Okay. If there aren't any questions, then I'll see some of you shortly, and I'll see the rest of you on Wednesday. If questions come up, just put them on Piazza, and we'll answer them.